So let me start with a definition. Okay, so let's let A be a subset of R. Let's let A be a subset of R. And open cover of A is a collection G is a collection G of open sets G alpha such that A is a subset of the union of G alpha. So what we are saying here is that a collection of open sets is an open cover for A if the union of the open sets in the collection covers all of A. A is inside of the union of all these open sets, okay? Then we call G to be an open cover, okay? Now if G prime, that's a subset of G, and G prime is an open cover of A, then G prime is called a subcover of G. So note that what is G prime? We are saying that if a subcollection of G also covers A, if a subcollection of G also covers A, then that subcollection is called a subcover of G, right? So G prime is a subcover of G if G prime also covers A. Okay, G prime is a subcollection of G. Now moreover, if we have that G prime is a finite subcollection of G, and G prime is an open cover of A, then G prime is called a finite subcover of G. Okay, so again, let me go over this definition here. So what is an open cover? Open cover means, for an open cover of A is just a collection of open sets such that the union of the collection contains A, and then we have a subcover, means it's a subcollection of the bigger cover or bigger open cover, and if the subcover is finite, it's called a finite subcover. Is that definition clear? So now the question, now I want to define what I mean by compact subset of the real numbers. So here's another definition. So so here's the definition of a compact set. A subset K of R is compact if every open cover of K, if every open cover of K has a finite subcover, has a finite subcover. So once again, a set K is compact if every open cover of K has a finite subcover. What does it mean? Anytime you come up with an open cover for K, it could be an infinite collection. There is always a finite subcollection which covers K. Okay? So that's when we call K to be a compact subset of R. Now, let's go over a few examples now. Let's take my first example to be, let's say the set A is the interval from 1 to infinity, okay? And so, so first of all, can you give me a open cover for this set? Can you give me an open cover for this set? If you take the set of all real numbers, that's an open cover, so you're right. So I can take G to be, if I take just the set of all real numbers, this is a collection where the collection has exactly, the collection G has exactly one open set in it. Okay? So this is an open cover of A. Can you give me an infinite open cover? Can you give me an infinite open cover? Infinite collection of open sets which will also cover A. Mm-hmm. Mm-hmm. Just an infinite collection of open sets which will also cover A. Was that?
I don't know. Can you do like 0 to 1 and then
Yeah.
1 to 2?
They have to be open, right?
Right.
So it's better probably to say,
You
yeah.
say like 1 to infinity, 2 to infinity.
But then how do you include 1? Because if you include 1, then it becomes a closed, right, not open.
Oh, right. So 0 to infinity, -1 to infinity, -2 to
Yeah.
infinity.
And in other words, I mean, something like this would work, right? 0 to 1, 0 to n, such that n is in n, right? Would that work? That's an open cover of A, right? As n goes to infinity, you cover all of the numbers between 1 to infinity, right? And in fact, you can also, instead of starting at 0, you can start at half or anything less than 1.
Right.
You could also say that I have the cover between, instead of taking 0 to n, I can take, say, from -n to n. So I'm taking basically bigger and bigger intervals, -1 to 1, then -2 to 2, -3 to 2, and so on. That will be also an open cover of A, right? Now, now let's ask the following question: is this interval from 1 to infinity, is it compact? So is the interval from 1 to infinity compact? What would you say? Is my interval from 1 to infinity, is that a compact subset of R? What is the meaning of compactness? It means that every open cover has a finite subcover. So anytime you have an open cover, it's got to have a finite subcover, right? So what would you say? Is this guy compact? If you think it is compact, then you have to show no matter what cover you start with, it always has a finite subcover. On the other hand, if you think that it's not compact, then you have to give me an example of a cover which has no finite subcover, right? So we have in the previously we said that we have two covers, right? But one of them we started with a finite cover, so of course it has a finite subcover. But the other one is an infinite open cover. So the question is, does it have a finite subcover? Can you say that G has a finite subcover? Right? Can you pick only finitely many sets from G which will also cover all of A? Is that making sense? What is the answer? No, because if I just pick finitely many, right? If I just pick finitely, so for example, let's say I pick G prime to be something like, say, 0 to n1, 0 to n2, up to, I don't know, 0 to nk, for example, where, let's say, here n1 is less than or equal to n2, less than or equal to nk, okay? Those are the type of intervals. But then, what is the union of the elements in G prime? What is the union of all this intervals? Well, the union is basically contained, right? It's basically contained in the interval from 0 to the biggest one, nk, right? And which does not cover, which cannot contain the interval from 1 to infinity. So the open cover G right here, it doesn't have a finite subcover, right? And that's enough to say that that this interval from 1 to infinity is not compact. Okay, so our conclusion is that 1 through infinity is not compact. You guys are okay with that? Any questions on that?
Well, I was just wondering, like, you labeled them both as G.
I labeled both of what?
Like both
Yeah,
are
maybe
open
let's
covers.
call that G1, I guess, or something.
I just
Yeah.
wanted to know.
I'm talking about the G, which is the infinite cover.
Right.
Yep. Is that okay? Again, for a set to be compact, every open cover must have a finite subcover. So we found a open cover which does not have a finite subcover. Therefore, this set cannot be compact. Okay.
So,
Yeah.
in order for us to say that
Mm-hmm.
G is an open cover of A,
G is an open cover means it's just a collection of open sets whose union contains A.
okay.
Yep.
So all the unions from like 0, 1, 0, 2, 0, 3,
Yeah.
the union of that would be
Contain all of it. Yep. So G is not compact in this case. Okay, good. Let's look at another example. Another example. Let's see if you can give me determine whether it's compact or not compact. Let's say my next set is let's say my next set is here, K. I'm going to take K to be just a finite set, okay? finite set of numbers. Let's call them x1, any finite set of real numbers. Maybe I have n of them, okay? Maybe I have n of them. So here, of course, the xi's, they are all real numbers. So all I'm saying is the k is a finite subset of the real numbers, and say, let's say it has n numbers, okay? Now, is k compact? Is k compact? Okay, what do you have to do to show that?
Every open cover has a
Finite subcover, right? Well, let's start with a open cover. Let's let G equals to the collection of G alphas be an open cover, be an open cover of K. Okay. You have to show that there exists a finite subcover of G, right? Finite subcover means it's a finite subcollection of G whose union also contains K, right? Okay, so how would you argue that you can just find a finitely many of them? How would you argue that? That is, you want to tell me that, hey, I can find finitely many G alpha whose union contains all the elements of K. Right? Right now we are saying the union of everything in G contains K. How do you argue that you can just find finitely many which will cover all of A, all of K?
K is finite, like K is finite.
Yeah, K is finite, I get this, but you still have to argue why. How do you know there are finitely many G alphas which will contain all of them? So what I need is a little bit more than just saying that it's finite, okay? Well, let's see what is the meaning that we are saying that G is an open cover of K. It means it means that K is inside of the union of G alpha, right? That's what it means. K is inside of G alpha, and all the G alphas are open sets, right? Now, doesn't it simply means then that x1 is inside of, well, if x1 is in K, right, then x1 is in the union. So x1 must be in one of the sets in the union, right? So x1, let's say, is in G alpha 1, okay? Same way I can say x2 must be in one of the G alpha 2, right? And so on, I can say xn would be in one of the G alpha n. So now I can define a subcollection G prime by saying it's G alpha 1 up to G alpha 2, sorry, G alpha n. G alpha n. Well, this is a finite subcover, right? This is a finite subcover. Is that making sense? So I could say that K is compact. So K is compact. Any questions? So from now on, anytime you have a set of finite subset of R, it's compact. Okay. Let's look at one more example. I think this is a important example. So this is the example where I'm going to take K to be the set of numbers which is the interval from 0 to 1. Just the interval from 0 to 1. Again, the same question, is K compact? What would you guess? What would be your guess? is K compact? If you think it is compact, you have to argue that any open cover has a finite subcover. If you think it's not compact, then you have to give me an example of an open cover that doesn't have any finite subcover.
Well,
Mm-hmm. Okay, that's a good start. Then give me a counterexample. Give me a counterexample that is, so by counterexample I mean give me an example of an open cover that doesn't have a finite subcover. Was that? Well, that's already a finite. That's already a finite cover, right? If you just take the interval from 0 to 1 in your collection G, it's already a finite cover. Of course, it has a finite subcover. But you're trying to show that you can find a. I mean, in order to show that it's not compact, you have to come up with an infinite cover, and show that it doesn't have a finite cover. Remember, 0 is not included, 1 is not included in my set. Every number in between is inside. Yes. All you have to do is guess. So let me just give you a hint that the collection G would be a collection of open intervals. Those are open sets, right?
Okay,
So can you, yeah.
Can we say
Can you give me a collection of open intervals which will cover all of this 0 to 1? Mm-hmm. Let's say you're going to use a counting number in somehow in this open intervals. Mm-hmm. Okay, 0 to 1 over n is close, but 0 to 1 over n, note that as n goes to infinity, 0 to 1 over n shrinks, right? So it cannot contain 0 to 1.
So
It's pretty close.
1 over n to 0 1.
Yes, 1 over n, 1 over n to 1, and look at that, n is a counting number, right? Let's see, 1 over n to 1, right? As n goes to infinity, 1 over n goes to 0, right? So this collection of open intervals, it covers all the numbers between 0 and 1, right? Of course, it doesn't, the number 0 is not covered by this open cover, but it doesn't matter because 0 is not in my set, okay? So this is an open cover. So G is an open cover of K. Now, how do you argue that there can't be a finite subcover?
Well, there exists epsilon such that.
Well, let's first see how a finite subcover would look like, right? If I take G prime to be a finite subcover, it's going to look like that I have 1 over, let's say, nk up to, sorry, let me just say the following. 1 over n1 up to 0, right? Not 0, sorry, 1. 1. 1 over n2 up to 1. Because all these intervals are of this form. Some 1 over some counting numbers up to 1. And so maybe I have all the way up to 1 over some nk up to 1. And let's just say that here n1 is less than or equal, less than, well, I don't want them to be the same, so less than n2, less than nk, okay? So now, any finite subcover will have to look like this, right? Now note that what is the union of the collections in G prime? So if I take the union of everything in G prime, right? So that would look like I have 1 over n, let's say j up to 1, and j goes from 1 to k, right? That's the union of everything in G prime, right? So what is that equal to? Could you tell me what is that equal to? So basically you have to figure out which one has the smallest left-hand point, right? Which one has the smallest left-hand point? Because that's going to include all the other ones. You see, nk is the biggest number here, right? Nk. So 1 over nk is the smallest left-hand point of these intervals, right? If I make a picture, you know, here it says 0, here is 1, and this 1 over nk, let's say right here, but the 1 over nj for any other j, 1 over nj will be to the right of 1 over nk, right? Because nk is bigger. So in fact, this guy includes all the other intervals, right? So the union is just 1 over nk up to 1. Well, and the question is, that union does not include everything from 0 to 1. So it does not include everything from 0 to 1. So my point is, no matter what subcollection G prime you pick, it cannot cover all of 0, 1. Okay? So the conclusion is the interval from 0 to 1 is not compact. Okay? See if you have any questions. Okay,
So,
yeah, go ahead.
Is it true that like any
Mhm.
interval that has like an infinite number of elements is not compact?
Any element, say it again.
Any interval that has like an infinite number of elements inside it would not be compact.
Well, not necessarily, because if I look at the interval from, pretty soon you're going to see that if I look at the interval from 0 to 1, including 0 and 1, that's compact. I didn't give you that example yet because I'm actually going to give you a general theorem right now. Yeah.
How about any open interval with an infinite number of elements?
Or open interval, by definition, there's lots of points there, right? It's already infinite. If you have an open interval, right, it's already an infinite set, right? Yeah. So anytime you have, you're right, anytime you have an open interval or an infinite interval, I think what you're getting at, instead of saying what you're saying, I think you're saying that if I have an interval which is an infinite interval, like 0 to infinity, negative infinity to 3, those are all not compact, right? And also any open interval will not be compact. So that's a good point. Let me actually write it down. So remark, any open interval is not compact. And how do you argue? You actually argue exactly the same way. In this case, all you have to do, for example, remember I took the, from 0 to 1, I took the open cover from 1 over n to 1. So if you have any interval from A to B, right, open interval, you can just take a cover like A plus 1 over n to B. Open intervals like A plus 1 over n to B, as n goes to infinity, it goes away, right? So that's going to be an open cover for the interval from A to B, for example. Yeah. Go ahead.
Okay, so I started thinking about, you said the closed interval from 0 to 1.
Closed interval from 0 to 1 will be compact.
Will be compact, but that's because it's countably infinite, right?
The interval from 0 to 1 is not countably infinite, right? It's
Okay.
an uncountable set. Both the open interval and the
Right.
closed interval from 0 to 1, they are uncountably infinite, right? They are uncountable sets.
Well, I mean, technically, it has a continuum is continuum.
Yeah, there is that those 0 and including those 0 and 1s, that's very important, okay? And if you think about it, those are actually the cluster points, right, for that. Now, what is the difference between the open interval from 0 to 1 and the closed interval? The open interval is just an open set, right? The closed interval is closed, not closed in the sense of a closed set. The interval from 0 to 1, if you just use the, what is it called, brackets, it's a closed set in the sense of the way we define what is it, the meaning of a closed set. And also it's a bounded set from 0 to 1. So I'm going to give you a theorem which says that a set is compact if and only if it is closed and bounded. Now remember, closeness means it contains all of the cluster points. So that's why including those 0 and 1s are important. Okay. So here is the theorem. So you are actually getting ahead of me. So this would be our main theorem here, and this is known as the Heine and I think Borel Heine-Borel theorem. Okay. We had a professor named Heine Halberstam in Illinois, and he was a pretty famous guy in number theory. I think he was a survivor of the Holocaust, and so he came to U.S. I think about that time from Europe. And he was very good at what he did. Okay? So
Is he related to this Heine guy?
no, no. He is not related to this guy, but I think he's from UK. Okay, but he was a survivor of the Holocaust. All right, so the theorem says very simple. It says that a subset K of R is compact if and only if K is closed. K is closed and bounded. So a subset K of R is compact if and only if K is closed and bounded. Now, this is not an easy theorem to prove. I mean, if you look at your text, it's 2 pages worth of proofs. Okay,
We can do
2 pages. So, but again, I want to explain to you the big ideas with pictures. Okay, so let's start the proof. Well, first of all, I want to show the direction that if K is compact, so we first show if K is compact. This is probably the hardest theorem you will see in the entire course, okay, to prove. If we first show that if K is compact, then K is closed.
Question.
Yeah,
My creative juices are going again.
yeah.
So you said this was probably the hardest one to prove.
Yeah, I mean, because it's pretty big.
Right.
Yeah.
What if we made a presentation on how to prove this? Could we supplement that in the last exam?
In your last exam, no, what I want you to do for your last exam is something different than what
Or,
I,
mean, not like our final, like our third exam before our final.
for your third exam.
Yeah.
Your third exam is not a presentation.
Right. Well, I'm asking, can we make it this presentation?
Oh, could this be, oh, yes, yes. Not for the final presentation,
No, not for
but
the final presentation.
before that, I'm going to have another presentation just like we had one before.
Oh, okay.
And then you could use that. Yeah. But one thing you could do is this topology part, if you present that in our student seminar, then I would give you some points, okay? Okay. So you are already,
Understand it first.
you already agree that you're going to give a talk on the
Yeah.
journal problem that
Yeah,
you solved,
yeah,
okay? So if you want to give a talk, and if you give a talk on this topology part, okay, then you can earn some points, okay? In the math seminar. So maybe math seminar, remember we have the student seminar means that it's a usual math seminar, but there will be pizza, all right? And he gave one last semester, I think, right?
Yeah, somehow one of my slides got messed up too. I was pretty
Right.
upset about it.
But
It's like,
since he has only one problem to present, now two of you can present on the same day. So think about it. If you want to give a talk in the seminar, then let me know. You can both go together.
okay, so since I've already agreed to do this,
You have to do only the problem, journal problem.
right, but since I've already agreed to do this, does that mean-
Yeah. I'll give you both points.
Okay,
Okay.
okay.
All right.
I didn't know if I was
All
exempt
right.
from getting points.
Yeah, I mean that problem is much harder than what you have done
Right.
here. So yes, sure.
What day did you pick again?
I did.
It has to be after the November 1st, because the journal problem is due by November 1st, so he can't speak about it before that.
Hmm.
Okay. So yeah, I mean, I think it's usually about 3 o'clock. So maybe you can go first, and then you can get out of there.
Okay.
Okay, and then he can go next. All right. So if you want to do it, let me know soon so that I can arrange that. Okay. All right. Let's get back to this proof. If we first show that if K is compact, then K is closed and bounded, right? All right. So so what do? Well, we assume K is compact, right? We assume K is compact. Assume K is compact. And I have to show that K is closed and bounded, right? How do I show K is closed and bounded? Well, I have to show two things. One is K is closed. The other one is I have to show that K is bounded. The easier step is to show that K is bounded, okay? So let's say I want to show K is bounded. How would I do it?
Show that there's
I want to see, showing that K is bounded means K has an upper bound or a lower bound. In other words, all I have to show is that whatever the set K is, let's say, all I have to show is that whatever the set K is, let's say K is from here all the way up to here on the real number line. Let's say that's the set. I don't know the composition of K. I'm just saying that K is some set. If I want to show that K is bounded, maybe all I have to show is that K lies between two numbers, negative m and m. Let's say 0 is here. Is that making sense? If I want to show you that K is bounded, all I have to show is that the entire set K, all the numbers in K lie between negative m and m. Right? So how do you relate that to the fact that we are assuming K is compact? Assuming K is compact, can you tell me that there is an m such that K is between negative m and m? How would you argue that? Of course, we are assuming K is compact. It has to do with covers, okay? You have to relate the boundedness with those covers, right? So,
Okay, so like we have the
Uh-huh.
finite sub-collection.
yes. Anytime you have an open cover, it has a finite subcover. Yeah.
So the smallest element that's in the
Mhm.
finite subcover would be plus sign equal to negative n, right?
In the finite, the smallest element in the finite subcover, but you have to come up with the cover first.
Oh, okay.
So first of all, can you give me a cover for K? Even though you don't know anything about K, right? Can you give me an open cover for K? How about you give me an open, infinite open cover? Good. So let's say I take G to be the collection of open covers, collection of open intervals like negative n up to n, and n is a counting number. Okay, so if I take the, is it clear that no matter what K is it, K is a subset of R, it's got to be inside of the union of all these intervals, right? Remember, n is going from 1 to infinity. That's very clear. In fact, this union covers all of R, right? It covers all of R. So it's got to cover K. Now, since K is compact, so G is an open cover of K, no matter what K is, since K is compact, we know that G has a finite subcover, right? G has a finite subcover. Well, what does that mean? It means that I have a finite subcover like G prime. A finite subcover of G looks like what? Does it look like negative n1 up to n1, negative n2 up to n2, right? And negative nk up to nk. And let's just assume that n1 is less than n2 is less than nk. You agree with that? If I have a finite subcover, it looks like all these intervals from negative n to n. So that's what I have. But then, what is the union of the intervals in G prime? So if I take the union of all these intervals in G, let's say I, let me just say I, and I is inside of G prime, right? That's the union of all the intervals like negative nj up to positive nj, and j goes from 1 to k. And can you tell me what does that equal to? It is, what is that equal to? It is equal to what? Because nk is the biggest, right? So what do we have? We have actually expanding intervals, right? So it's like negative 1 to 1, negative 2 to 2, negative 3 to 3. So negative nk to nk includes all the other intervals here. So this is negative nk up to nk. Yes. The intervals that we have here is a nested interval. The last one includes the previous one includes the previous to that one, okay? So that's what we have. But then it's a finite subcover, that is k is inside there, right? Well, it means that k is in the interval between negative nk and nk, so that's k is bounded. So k is bounded. Okay? Now we have more to go. I have to show k is closed. So that only shows one way. K is compact if and only if this. Then I have to show that if k is closed and bounded, then it is compact, right? So we are going to do the rest on Friday, okay?